First of all, delighted to have this opportunity to speak at the Energy Institute today. I gave a talk at Texas A&M just before the pandemic shut down. Well, maybe not just before, but about a month or two before, on power grids, and it was a fairly high-level talk. So I thought here, when I was thinking about this, what I talk about here, I thought I might do get a little bit more down in the weeds of some of the things that we're doing in my group here at Princeton. And in particular, I want to talk about a collection of things that relate to the use of graph-theoretic methods to look at various properties of power grids. And of course, real power grids are very complicated things, cyber physical systems. Of course, it's big. The physical part is a huge electromechanical system, often said to be the largest and most complex machine in the world. And I think that's a fair characterization of the U.S. grid. And so it's very complex, and understanding it, of course, is an art, and the people who do understand it well are people who have been studying it for years and working in the field, which is not me really. I'm really much more of a theoretician, as Jeff said, but I've tried to use some of the tools that I know from various other problems I've worked on to look at some aspects of power grid, but realizing, of course, that this is an abstraction, but hopefully allowing us to gain some degree of understanding of power grid behavior. So that's really what I'm going to talk about today: a collection of results hang together through the fact that they all have something to do with using graphs to represent power grids. So, the work I'm going to talk about today is work with multiple people. One is Yuzhu Chen, who's a postdoc in my group right now. He's a statistician. He got his PhD at SMU. Asim Day, who is a professor at UTEP, also got his PhD at University of Texas at Dallas, also in statistics. So he also is a postdoc briefly with me. Yulia Gell, who's a professor at UT Dallas in statistics. Andrea Goldsmith, who is, at the time I was working with her on this, was a professor at Stanford. Now she's at Princeton. She's my colleague here. And she's also the Dean of Engineering here at Princeton. And then Yue Zhao, who was an electrical engineer, got his PhD at UCLA. I did a postdoc with both Andrea and myself when she was at Stanford, so it was a bi-coastal postdoc, and now he's at SUNY Stony Brook. So anyway, these are some of the people. There are a couple of others whose names will pop up here and there, but this is joint work with them over a period of about 5 years, I guess, roughly. And I'll point to some particular papers as we go along. So, here's the basic premise. So a power grid, of course, as I said, is a very, very complicated thing. But one thing it is, it defines a graph. Okay, so you could think about the assets on the grid, like generators or what have you, as being nodes in a graph, and then they're connected by lines. Okay, so if it's a transmission grid, the nodes are the generating resources, and the lines are transmission lines. If it's a distribution grid, maybe the nodes are loads and other things down in the distribution grid, and they're connected by lines also. Okay, so, and it's a planar graph, so it's a graph that sits on the plane pretty much. And that's a very abstract way to look at the grid. It's just to extract this graph that describes basically its topology. So the question I'm going to address today is sort of what, in part anyway, is what can that graph tell us about grid resilience, and a few other things I'm going to talk about as well. So let me just check the chat, make sure. Okay, I got it. I just want to make sure people can hear me okay. All right, so anyway, so we have this graph. It's a very simple thing, describes a very complicated thing. And the question is, what can that tell us about resilience and other properties of the grid? So here's an outline of particularly what I'm going to talk about. I'm going to talk about, first of all, start out by talking about some grid property known as motifs, and how that can be used to assess robustness or resilience of a grid. I'll define that in a minute. And then I'm going to talk about some other grid graph properties, higher order topological properties of a grid, simplexes or simplices, and persistent homology, two other properties, and how they affect robustness. And then that's the main part of my talk. And then depending on how much time I have, I want to talk about two other things just very briefly. One is online detection of topology changes. So you have a graph and the graph changes. How do you detect that quickly? So for example, if there's an outage or what have you, an attack. And then the other is has sort of related problem, which is how you can look at the graphical structure of the grid and determine what is the optimal attack construction for an attacker who wants to attack the grid, and conversely, what can you do to mitigate that? Okay, so those are only going to be very, very brief, but let's see how it goes. All right, so let's start talking about motifs and robustness, and this is work with Asim and Yulia, and also with Yuzhu and Tony Ng, was his professor at SMU. So here's some basic motivation. First of all, what do we mean by the resilience of a network? Well, it's usually tolerance to perturbations. So in the case of a grid, that's tolerance to, say, a generator tripping or some other asset being taken off the grid. Now, there are, just looking at networks in general, network science in general, there's a lot of work on graph-based resilience. And they typically use what are called global network characteristics, which are, for example, you may be familiar with if you've looked at work on network science, the so-called giant component of the graph, the degree distribution, the out degree, for example, the so-called clustering coefficient, and so forth. So these are all, a lot of these things came up. These came up when people were looking at small worlds, graphs back 20, 30 years ago. And then they also can be used to look at resilience, okay? But there have been studies that have shown that grid resilience is also intrinsically connected to higher local properties, not these more general properties, and higher order topological properties. And I'll give some examples in a minute. So here we're gonna start with a hypothesis that the grid's resilience can be quantified in terms of its ability to maintain its original topological properties. So in other words, if you start destroying those topological properties, you're basically the grid is losing resilience. And so I'm going to look at this in the context of several such higher order topological properties. As I said before, network motifs, simplicial complexes or simplexes, and topological data analysis, or persistent homology is the particular tool, okay? And I'll start out by focusing on motifs, and I'll look at some of these other things in a minute. Okay, so what are motifs? Well, if you have a planar grid, a graph, then we can look at small subgraphs within the graph, and those are called network motifs. So there's 3-node motifs, excuse me, 4-node motifs, 5-node motifs, and so forth. In here, I'm showing the T's here on the left are all the 3-node motifs, and the M's are the 6 4-node motifs that can appear in a graph. So you might think about if these were connections between nodes on a grid, you might think about how these could be somehow related to resilience. So look, for example, at T2. If you have that connection, that seems more resilient than T1, right? Because if in T1, if the corner went out, that disconnects the grid, whereas in T2, if the corner went out, the other two nodes would still be connected, and so forth for the other motifs. So there is some intuition that motifs have something to do with the resilience of a graph, and thus with the resilience of a grid. So how can we look at this in the context of grid resilience? Okay, so one thing is we can take a graph that describes the grid and look at how the motifs, look at the count of motifs. So how many, say, how many motifs of a certain type do we have? And then look at how that declines as we start taking nodes out in some organized way. Okay, so obviously you start the nodes, you can only lose motifs if you take nodes out. So there's going to be a declining count of motifs as you sort of say attack the grid in a certain way by taking out nodes. Okay, and we can, so that's a way to gather data, but we can model we can model that statistically by what's called a gamma degradation process. So it's just a model for processes like that where you have a monotone decreasing quantity, and that represents degradation. So it's a parameterized process. I didn't put the details here because it's not that important. Okay, but it allows us to capture this monotonicity of the decline of the motifs. It also allows us to capture dependence among motifs, and it's also computationally very straightforward. Okay, so this is a statistical method to capture something about what happens to the grid when as you start taking nodes out. Okay, so this is a statistical model. We can do statistical inference based on the motif counts to estimate parameters of this degradation process. And then we can use those estimates to assess grid resilience. Okay, so that's basically what we're going to do. And I'm going to look at two different cases. One is a set of European power grids. These are the transmission grids of various countries in Europe: France, Germany, Italy, Poland, Romania, and Spain. Those graphs are found online, put out by this European Union for the Coordination of the Transport of Electricity. And you can see here in this table the number of nodes on these graphs and the number of edges, and we know the topology. And we're going to focus in these graphs on the particular 4-node motif shown there on the slide. And why those 4 and not the other 2? Well, it's because these are the only 4 that appear in all of these grids. So not every motif is necessarily going to appear in every graph. And those other 2 that are not shown here don't appear in some of these graphs. So we're just going to stick with the ones that appear everywhere. Now, I mentioned that some of these other graph-theoretic metrics of vulnerability don't really capture the reliability that well. And I mentioned betweenness, I didn't mention diameter, but betweenness is one, clustering coefficient is one, degree distribution. There's a whole bunch of them. And for these grids, we calculated 6 of them. And basically, they're all over the place. So just like I said at the beginning, these are not really conclusive on grid robustness. These sort of big global power grid graph properties. Okay, so that's one of the things that motivates looking at these more local properties like motifs. So now let's look at the motifs. So suppose we start attacking these grids by removing nodes in decreasing order of their degree. So we take out the highest degree node first, the next highest degree node second, and so forth. And we just do that until we've taken out 10 nodes, 10% of the nodes, so 1%, 2%, and so forth. And we just count the number of 4-node motifs of these 4 types, the remaining for these 6 grids. and we get these charts that you see here, okay? And you can see here that these different motifs decay with different rates, and it looks like different countries have different characteristics as to how many, what percentage of these motifs remain after attack a certain level, okay? Now we can use this data to do hypothesis testing and to try to cluster these countries in terms of how their degree, the decrease in motifs behaves, okay? And so if we do that, we can put together a heat map using a t-test, so the p-values. And by doing that, we see that there actually are three clusters in these countries. Italy and Germany cluster together, Romania and Poland cluster together, and France and Spain cluster together. That is, in terms of how they behave against this degree-based attack, in terms of how the motifs survive, these are sort of similar, these three different kinds. They're different from one another, but they're similar, they're different from within, the clusters are different from one another, but within a cluster, they're very similar in how they behave. Okay, but that doesn't tell us which one's better, which one's worse. It just tells us that these are, Italy and Germany are similar in this regard and so forth. But we can then do the statistical testing based on this degradation model to actually see which ones might be better in terms of persistence or resilience, okay? So in particular, there are parameters in this degradation model that I mentioned, and those parameters involve rates of decay, okay? And they're lambdas. And so we can aggregate them into, the details are not here, they're in the paper that I mentioned, but I don't think they're that important. So we can basically look at an average rate of decay for a given grid, call it AI bar. And the smaller that is, the more robust the network is, because that means that it persists, the structure persists longer as you start attacking it, taking out these nodes based on their degree. And so here we did that for these 6 countries. And you can see that, in fact, the clusters hold up, the ones that we determined from just looking at how the motif distributions declined with attack. And in fact, Germany and Italy cluster together, Poland and Romania, France and Spain. And Germany and Italy have the lowest A bar. So that means their structure persists the longest under attack. So they're actually the most resilient in this respect, whereas Poland and Romania are less resilient and France and Spain are less resilient. Okay, so here's a simple way to analyze the resilience of the grid based on these motif distributions and the statistical model. Now we can look at another case study, and the reason I want to do this is because we don't really have any evidence, just back up, we don't really have any evidence necessarily that although we think that Germany and Italy are more resilient based on our analysis, we don't have any evidence that our analysis is any better than anybody else's, right? So one thing we can do to do that is we could look at other grids where we know more than just the graph. So for these European grids, we only know the graphs, but there are grids, synthetic grids at least, where we know more about the physical characteristics. And 2 of these synthetic grids are the South Carolina, the sort of active-S grids, the one in South Carolina that models South Carolina, it's based on the actual physical grid, and the Texas 2000, also based on the actual physical grid in Texas. And these are synthetic grids, but they have all the characteristics of a grid. They're not just a graph, okay? So what we can do is we can look at our technique, and then we could look at some more standard measures of reliability, loss of load probability, and expected unserved energy, which we can compute for these 2 grids. We can't for the European grids. And then we can feed those into our model and see how they compare to this motif looking at motif distributions. Okay, and when we do that, here's what we get. So on the one hand, we feed in for these grids, we attack them, degree-based attacks. We look at the 4-node motifs and do the same thing we just did. And then we look at we take mean LOLP and mean EUE and put that into the model together, and we see what parameters we get. Okay, and you can see that basically we get the same ordering. That is, if you're looking just at motifs, we get the same conclusion that the South Carolina grid is more resilient than the Texas grid, at least in these synthetic models. And that's also what the more traditional measures based on physical characteristics give us. So a conclusion we can draw is that, at least for these examples, network motifs and these more physical measures of grid resilience yield similar conclusions on robustness. And the advantage of our model is that we just use the graph. We didn't use anything else about the grid. So that means just by extracting the graph, or if we only have the graph, like in these European grids, we can still run our test for resilience on that grid. So this is a bit of a confirmation that what we're getting at is something like resilience as measured with more complex data. Now, so motifs is one kind of higher order topological structure that we can look at. There are others, as I mentioned, and now I'm going to talk a little bit about how we can take advantage of those. So we just got through seeing that rate of degradation of motifs distributions gives us a way of assessing grid resilience. So, but I also mentioned at the very beginning, there are other ways of assessing higher order topological properties of a graph. One is looking at simplicial complexes. Another is topological data analysis. Okay. Now, I started out with motif because that's something we can easily analyze. It's a simple concept. Motif distributions, very simple to count. There's algorithms, simple algorithms for counting motifs. And there's a good model for degradation, a good statistical model. So we can just use a statistical model using motifs. On the other hand, as we'll see, these other techniques are much more complex. Okay, they're really diving much more deeply into the structure of the graph, and they're not easily amenable to statistical modeling. So then we need to turn to something besides statistical inference, traditional statistical inference, to make headway in terms of using these ideas. And so we're going to use neural networks. Okay, so it's a natural way to go beyond when you have data, but you don't have a good model. Neural networks is a natural way to proceed. So first of all, let me say a little bit about these other structures. So simplicial complexes, and I'll just motivate it here. If you look at this, so first of all, the motifs are planar structures. Okay, that is, they are two-dimensional. Okay, so the graph is two-dimensional. We're extracting two-dimensional information with the motifs. But if you think about a grid, even a distribution grid, say, if you have, say, look at this little, square here. So suppose all the vertices are assets of some sort, loads or generators or what have you. And the actual connectivity is shown in the dark lines. I don't know if you can see my pointer, but I'm pointing at this thing right here. So the dark lines here show the actual connectivity. And so there's a 4 motif there. But actually there is sort of an influence between, say, this lower node and the top node. It's through these other nodes. But if this, for example, were a substation down here at the bottom and it were to go out, well, it would affect this top node, right? Or if something else happened, it would affect this top node. So there's actually more structure here than we can capture with the motifs, but it's a little more nebulous. But that kind of higher sort of multi-dimensional structure, it's not two-dimensional. We can think of it as a 3-dimensional structure. And that kind of structure can be captured through what are called simplicial complexes. So you could have a node is a 0 simplex, 2 nodes connected with a vertex is a 1 simplex. A 3 motif is a 2 simplex. And then a 3 simplex, though, gets beyond what we can do in a planar fashion. We have to start building multidimensional structures. And this is like a pyramid. A 3 simplex is like a pyramid. Okay. And in addition to, there are other properties we can give to simplices. I'm not going to talk about it here today, but we can also give them structure. Look at the faces, for example, here in the 3 simplex, there are these facets. Those facets can be given properties as well. So unlike in just a plain graph where you might give properties to the edges, here you have more structure that you can define. So those are simplicial complexes. Now, topological data analysis is a bit more complicated, but it's related to this. So basically, TDA is a fairly recently emerging way of looking at graphs, analyzing graphs and other data sets, which involves, a lot of different things: machine learning, statistics, algebraic topology. So puts a lot of things together, and it's looking to try to look at structure in data at multiple resolutions. So shape structure at multiple resolutions, and it's a way of understanding the role of topology more deeply than just looking at motifs, for example. So one of the main tools is called persistent homology, which I mentioned before. I'll say a little bit more about that in a second. And basically what that does is it studies how shape structure changes at multiple resolutions. Okay, so maybe I can explain it better with a picture. So in the shape structure and persistent homology is based on simplicial complexes. So it's related to the first topic, the first thing that I just mentioned. Okay. So here's maybe another way to think about it. You could start with data. These could be like the nodes on a grid. And then you start building larger and larger neighborhoods of those nodes using some metric or some filter, so-called filter. And as you do, you get more and more structure. And so this sort of, as you build, as you allow the nodes to have more and more interaction, you can build these more complex structures. Okay, so it's a little, maybe a little hard to understand at first if you haven't seen it before, but it's ultimately a fairly simple idea. And then from these structures, so this is called the persistent homology. This how the structures that persist through these kinds of changes. And then you can extract summaries from that and get some data that you can actually put into a machine learning algorithm. Okay, so that's basically how persistence works into study of graph resilience. So we need numbers. If we're going to run a neural network, we need numbers. So simplices are not numbers. Clearly this nested structure of complexes, these are not numbers. So we have to extract some kind of features and numbers from this to make it work. So it's easy with simplices. So you probably are familiar with the graph Laplacian, which is just a matrix that tells us something about the connectivity of nodes in a graph. It's important to know whether the graph is fully connected, for example. That's determined by the eigenstructure of the graph Laplacian. But there are more complicated Laplacians. They're called the Hodge Laplacians. And the 0 Hodge Laplacian is the graph Laplacian. Then there's a 1 Laplacian, a 2 Laplacian, and so forth. So the graph Laplacian looks at relationships between nodes. The 1 Laplacian adds edges. The 2 Laplacian adds these facets that I mentioned before, and so forth. So the important thing so it's a way of characterizing simplices. And the way to think about it here is, bottom line is, it gives us a way to extract numerical information from the simplicial structure of the graph. So we can get a matrix. So this Laplacian it can be represented as a matrix, basically. So we can extract structure into matrix form that we can then use for machine learning. That's really the point of this. And the same thing with the persistent homology. In its basic form, it's very hard to use in any quantitative way, but we can, from a graph, we can derive what's called a persistence diagram, which looks at it's sort of a plot of birth versus death time versus death time for structure that appears in the homology or in the this nested series of structures. And then we can take that persistence diagram and mapping it into an image just using Gaussian smoothing. So this is just a technique for generating an image from a graph that captures somehow part of this idea of persistent homology. Okay. And then we get different, depending on how we let the graph grow, we could use degree-based growth, betweenness-based growth, closeness-based growth, and so forth. Each of these is called a filter. We get different persistence images. Okay, so the same graph can give different images depending on how we structure the growth of the neighborhoods, say, around nodes. All right, so we have from simplices, we can extract this graph Laplacian. From the persistent homology, we can extract these images. And then we can put it all into a neural network to try to develop a way of assessing grid resilience. Okay, and I'll say a bit more about that in a second. And don't worry about the details here. Basically, this is an architecture that can be used for that. The top architecture uses higher order convolution, HOSC, it is higher order simplicical convolution. Its input to the top layer is the k-Hodge Laplacian. In this case, we're going to use the 1-Hodge Laplacian, but basically you take the graph, you extract the Hodge Laplacian of a given order, that gives you a matrix. Then it can be used as input to a neural network, and this is the network. And the below part, the bottom diagram, we take the grid or the graph, use different filters, extract these persistence images. Then we use neural networks to get to extract features from those images. So this is what neural networks are good at, is processing images. Then we derive a few more structures, drive a few more observables, and then we have an observable based on the Hodge Laplacian. We have observable based on these persistence diagrams or persistence images. And then we take that as output of one neural network, and then we use an attention mechanism. Okay, so this is a fairly recently developed machine learning technique for looking at how different sequences relate to one another. Okay, so we do that, we put that into a multi-level perceptron, and that gives us a determination of how resilient the grid is. Okay, so it's very complicated. It looks like a kludge, but it turns out it works. Okay, as we'll see, at least in our experiments. Okay, so there's method to this madness, but I'll let it stop it there in terms of the structure of this. So here's a experimental result. So what do we do? What are we doing here? So first of all we're looking at different grids. So the IEEE 37 bus, the IEEE 123 bus, 342 bus low voltage network. And we're comparing this structure that I just showed you to a whole bunch of other techniques from the literature. So these do all kinds of things: graph neural networks, graph convolutional nets, message passing, and so forth. These are all from the relatively recent literature. And what we're doing here is we're looking at these grids, we're attacking them, and we're looking at the flow, resulting flow. And when the flow falls below a given level, a given threshold, we say the grid is an outage. And if it's above that, we say it's okay. And so there's a 0, 1 that we're trying to determine based on these grids. As we do that, so we train the network, and then we apply it on some new data. And you can see that we get very, very good performance from this more complicated neural networks than we get from any of these others. It's the best of all the ones that are out in literature. Okay. Now you might ask, well, this is pretty complicated. Do we need all of these inputs? Do we need all these properties? Do we need the attention mechanism and so forth? So we did an ablation study where we took out some of these things to see how it compared. Okay, so now this is looking only at our structure, but taking parts of it out. So hot nets is what we call this structure. And then, well, first of all, NT nets is something that's a little bit like using motifs. Okay, so you might think about that as being what happens if we were to go back to the first thing I talked about and use motifs. Okay, and you can see that there's a drop in performance here in both cases, 37 bus and 123 bus cases. And then we look at, and ET nets is another example. I didn't talk about it, but that's where we use edges only. Okay, also not performing as well. And then we looked at our network taking various things out. So if we take out the attention mechanism at the end, we lose performance. If we take out, if we don't look at the topology, that is the TDA, the homology, we lose performance. And if we don't look at the Hodge Laplacian, I'm sorry, if we don't look at the yeah, I don't know what the difference one is with and without topology. I don't remember what the difference is in there. But basically, if you don't include everything, you lose performance, essentially. Okay, so there's method to that madness, as I said before. Okay, so I got about 5 more minutes, so I think I can wrap up in 5 minutes. So I'll spend a little bit of time on 2 other issues, and then I'll take time for questions if there are any. So first of all, I'm going to talk about 2 things. So the first one is going to be, as I said, online detection of topology changes. So this is a slightly different problem now. So suppose you have a grid, and like happens in New Jersey fairly frequently, part of the grid goes down. Okay, if there's a hurricane off the coast, we typically lose a big piece of the grid. Okay, or if some line trips or something happens like that. Okay, so there's a problem. So one way to mitigate that cascading is to quickly detect it and island off that piece of the grid. Okay, but it's not necessarily easy to quickly detect it. I learned talking to some people from PSE&G, our power company here, that the main way they determine what parts of the grid are down is when customers report outage. So they don't have it instrumented in the way that allows them to do that. So and one reason is because the complexity is quite high. So I don't know about that part of the problem, but the complexity of actually doing the detection is also quite high. If you have say K lines in your grid, K is going to be pretty large. The complexity of detecting which grid is down is 2 to the K. Basically, it's a search, 2 to the K search over 2 to the K hypotheses. So that means that, you know, to do that in real time is virtually impossible, right? So one thing we can do is to try to find a lower complexity way of doing that. And so here's just one way of doing that. We can, first of all, now I'm going to use a little bit more. The topology here is, the graph is encapsulated in the incidence matrix, M. Now we're going to have power flows. So now we have a little bit more information than in the previous examples. And if we have this model for observations in the grid, then so S here is a binary line statuses. So that's 1 if a line's up and 0 if it's down. Then if we want to detect which lines are up and which lines are down, we have to compute the likelihood function of this and find the maximum over S to determine which vector of line outages and line non-outages describes the current grid. Okay, so this has combinatorial complexity. Okay, it's very, very difficult to do that. So what can we do? We can do that if we have time, but if we want to do that in real time, it's difficult. So one thing we can do is something called learning to infer. Okay, and this is work with Yui Zhao and another Chen, not the same Chen, John Su Chen, one of Yui's students. And here what we do is we approximate the posterior distribution of line outage, of a given outage vector with a parametric model, okay, say a neural network. And then we train that neural network offline. If we know the topology of the grid, we can sort through all the possible line outages and you know, in offline and fit this model to give us an approximation to the posterior distribution of line outage. Okay, now, that takes a long time. We have to go through all possible combinations and everything. But if we're doing that when the sun's shining, then where the hurricane, we'll have that model and we can very quickly apply it. We don't have to go through all that search to find the proper line outages. Okay, so that's the basic idea. Offline, we do training. Online, we just do we use this parameterized model, which could be a neural network, to do the detection. Okay, so here's just an example. It's a small example, 30 bus IEEE system. We use a 2-layer neural network as the model, the approximate model. And here's some parameters that we use. It takes most of an hour to train the thing, but less than a millisecond to make a decision once something happens. Okay, so that's really what we're after. Okay, and here it just shows what happens as we increase the data size, that is the number of the training data and so forth, and also as we look at the as we let the number of neurons in the hidden layer go up. Okay, so it works pretty well. But the main bottom line here is it takes a long time to train, very quick to make a decision. And then finally, and then I'll wrap up and take questions. Another problem is attack construction that we can use the graph for. Just very briefly, because we don't have much time, I mean, you know, there's two kinds of attacks that we can worry about. Cyber attack, where you do data injection. The attacker tries to fool the grid operator about the state of the grid without actually changing the state of the grid, right? So this compromised situational awareness. And there's physical attacks where you actually want to change the state of the grid without changing state estimate, so the operator doesn't know that the grid has changed. Okay, so you know, the goal of attackers in either case is, first of all, minimal detectability. You don't want to be detected making an attack. You don't want to be any more complex than you have to be, so minimal complexity, and maximal impact. You want to somehow maximally impact the grid with your minimal investment and with minimal detectability. And one way that we can get at that is to use the graph structure of the grid. And I'll just very briefly, we can set that minimum sparseness. We're looking for minimum sparseness without observability. We can set up an optimization problem to do that. And we can basically show that the solution to that problem is what's called the vertex connectivity. Okay, that tells us what is the minimum sparseness. So we construct a graph here. This is actually a weighted graph where we put the reactances on the graph. So it's a little bit more complicated than the graphs we're talking about at the beginning. And the impact, and that has to do, the graph actually includes PMUs. Okay, so if we have sensors, we change the graph, and that affects the sparsity and the impact of the attack. Okay, this can also be done for data injection attacks. That's an older paper with one of my former postdocs, but I'll just give an example and then that's it. So this just shows versus the number of PMUs that we put in a grid. This is again the IEEE 30 bus system. It shows us the number of buses that can be attacked successfully for a given level of sparseness. So for minimal sparseness, which is the blue line, you can't really affect many. You can't affect many lines, and if you put enough PMUs, you can't affect any lines or any nodes. Sorry. And then if you allow different degrees of sparseness, higher and higher sparseness, you can attack more and more. You can successfully attack more and more nodes. Okay, so sorry I'm going over this quickly, but I want to leave time for questions. All right, so let me wrap up. So what have we talked about today? We talked about some graph-theoretic methods. of analyzing grid properties. First of all, I talked about using higher order structures for assessing resilience. So started out with Motifs, fairly straightforward, allows for statistical inference. Then we introduced simplicial complexes and persistent homology, more complex and deeper structure. There we had to use neural networks, but in both cases it worked pretty well. Then we looked at these other problems just very quickly, quick detection of line outages using this inferential method by doing offline training and online detection. And then also characterization of sparse attacks, where we saw that the vertex connectivity tells us of a graph, tells us something about the capability of an attacker to attack at a given level of sparseness. Now, some other problems we didn't talk about here, these networks are all static, except the case of the topology detection one. So one thing is networks, of course, are dynamic. So adding timestamps to the graphs, let the graphs evolve in time, adds another degree of difficulty, but maybe is a little more realistic and applicable. And then also, this is maybe relevant to what happened in Texas when the grid went down, considering multi-layer networks that are independent. So like the gas infrastructure and the electrical infrastructure, of course, are very interdependent. And so maybe trying to understand how they interact using some multi-layer networks might be of useful in providing insights into those problems. And then finally, I'll just throw up some references. I think I mentioned all of these going through. These are basically references covering those things I talked about today, and I'm happy to share these slides with anyone who wants to look more carefully at these references. And with that, I'm done, and I'm happy to take questions.